The stage is yours,
Okay.
Kyle. It's yours.
All right. Thanks, everyone. Appreciate you being here. And I just have to give a shout out to the first speaker, James. I am also very interested and active in the local first space. I've heard James speak a number of times at those meetups and seen him participate in a lot of the discords. It's a fantastic community, and he's definitely one of the leading voices in that space. So I encourage everyone, if you've been interested in local first, you have yet another speaker who's echoing that we really do believe this is the future of the web and of software development. And I work for another company in that space. I just recently started a company called Source, and we also make database and synchronization things. We have some different takes than Electric SQL, but there's a lot of fantastic options in that space. So with that out of the way, I'm not going to talk about local first at all. We're going to talk about some functional programming concepts, specifically around the composition of data. This is something that has come up a whole bunch of times. I've been asked this over and over again, and I've had different code samples and gists that I like drop for people. I've written blog posts, and I decided I really just want to have like one canonical place where I give this talk so that I can refer people back, because this comes up a lot, and I would imagine many of you have probably run into issues like this. And I want to say that even though I'm going to use JavaScript, there are bits and pieces of what I'm going to describe today that are somewhat special or somewhat related to JavaScript, but a lot of these concepts are really broadly applicable to a lot of languages. So the goal is to understand those concepts, be able to apply them in JavaScript if you're working in JavaScript, but hopefully at least have the right terminologies, the right libraries, the right kinds of concepts to look for if you happen to work in other stacks. So with that said, let's dive in. I'm going to set us up with a running example. We have one single running example that I'll go through in all the slides, and we'll approach it in various different ways. So here's some setup code. A little small. I'm going to give you a moment to kind of grok what you're seeing here, but this is just some real basic setup stuff. I'll direct your attention to the bottom, the get mock data. I'm not doing any asynchronous API calls or anything like that. So we're going to literally just for these examples look at synchronous data that's already there, but we're going to treat it as if it could have come from somewhere else. And by the end, we'll actually be able to have abstracted that away, that it wouldn't matter if that was some asynchronous API call that we've gotten to. But to keep the code simple and straightforward, here's what we're going to work with. So the lookup movie it's a synchronous function that just grabs stuff out of that object that's in the mock data variable. And so that's the context that it's always going to be referring back to this list. I just pulled out a couple of globally known movies from the last 100 or so years and kind of put them into a list. So this is our basic example we'll go through. Let me direct your attention to the three functions in the middle: valid movie, recent movie, and format movie. We're going to be using those in various combinations along with the look at movie function. So that will kind of define our flow of data. Note that valid movie and recent movie are what we call predicates in functional programming. You probably know that term. It just means they return Boolean. So they're used to make decisions. We pass in a piece of data, we make some decision about it, and we say true or false. Lookup movie and format movie are different. They're not predicates, they're mappers. Their job is to transform data. So they take in something like movie data and return something else. And so, for example, the lookup movie takes in a movie ID and returns an object, whether it had to go through some steps like an API call, it just returns as an object. So that was one transformation. And then we transform from a movie data entry into, in this case, a string that just prints out the movie title and then the year it was released in parentheses. So we've got predicates and mappers. Those are the kinds of items that we end up in our application code kind of working with. That's our setup. And then we will start by kind of as our baseline, implementing a very simple data flow that will do so in the imperative coding style. In the context of the code and of programming, this term imperative, it gets thrown around a lot, but it means code's primary objective is to express how to do something. The reader has to mentally execute the code and then infer its purpose, the what or the why, after doing so. they can also optionally pick up on context clues such as the identifier names, the code comments, etc. And that style is contrasted with declarative, which is code that focuses more on the what and the why and allows something lower in the abstraction stack to handle the how. So the goal of most programmers is to try to elevate to a more declarative plane of abstraction. There are a variety of ways that we do that, and by a variety, I mean nearly infinite. And it should be seen not as a binary one or the other, but as a spectrum. You are either more imperative or more declarative, and it's also highly context sensitive. So one piece of code objectively can be viewed both subjectively as imperative or declarative, depending on the position that you're looking at it from. So we're going to start with what would be traditionally considered the imperative approach. Imperative is often characterized by for loops and if statements. So that's what you'll notice here. What we want to do is go through our list of movie IDs. We want to check to make sure that we have a valid movie ID because we might have some junk data in there. Then we want to look up the movie, get the movie data entry from that movie. And then if that movie is recent, meaning that it was returned since the year 2000, I don't know the relative ages of the audience here, but I'm going to imagine that most of us remember movies before 2000, but let's just call 2000 and later as recent for the purposes of this discussion. And then if it is one of the recent movies, format that movie data entry into the string and push it into an array. And then once we have that full array, and just for the sake of illustration, I'm console logging it out here. Okay. So that is our imperative approach. You see for loops, you see if statements. That is the kind of application code that many people write. Whether you use JavaScript or not, most people tend to default to writing that way. Functional programmers look at that and sometimes kind of cringe and say, ugh, there's a lot of imperativeness going on there. And we don't just say imperativeness because we don't like the code style. Because quite honestly, I actually think that for loops and if statements are not evil. I think they have their place in our programming. But the real reason why we're frustrated as a functional programmer with those things, and many of you I think will resonate, is that we look at those things and we say, oh, well, what that's accomplishing could have these little corners that I'm not really sure. Like I have to really trace through and make sure that there's no gotchas in the code because I don't have the assumptions and the assertions that these mathematical constructs from functional programming give us. So that's the main reason why we might want to elevate this code. It is ugly, but I think we can point out that, again, in the context of JavaScript, this is just about as performant as you can get for processing through the list in this particular case. It's at least in the context of a finite list that is already present of our movie IDs. This is just about the fastest way you can do that. Now, if we had an infinite stream of data, different story, and we'll talk about that later. But if we wanted to process everything eagerly, all right up front, this is kind of the lowest cost, the nearest to zero cost that we could probably do that. That's good that it has a good performance profile, but again, because it doesn't really use the abstractions that we know to have mathematical properties available to them, sometimes we might say this is a little less than ideal. So let's move into some of our patterns. We're going to start by talking about composition. Now, in programming and actually in the whole world, composition can be, it's one of those words can be used in like a million different ways. And even in programming, be used in means lots of different things. As it relates to this talk, we mean expressing and managing the flow of data through the program. That's what we mean by composition. And we want to express it and also to be able to operate on that expression, meaning to take one composition, one data flow, and augment it. Say, I want, now that it comes here, I want it to also go here, right? So adding on to the end of it. That's what we mean by expressing and managing the flow of data. We're going to talk first about a technique for composition, which again in JavaScript comes through the way of methods on the array values. So arrays, lists, for others from other programming languages. Arrays expose these things like map, reduce, filter, which we'll see here. And what we're saying is that by chaining those arrays together, you are creating a composition. It's a form of composition called method composition. So we could express the same imperative code from before in this style using those filters and map functions. Now notice the alternation here. That's going to be actually really important. We have a dot filter, which is making a decision on is it a valid movie. And then once we've decided that it's a valid movie, we've reduced our list down to a smaller context of only the valid movie IDs. And then we map those valid movie IDs into the movie entries through lookup movie. And then we make another set of decisions, taking those movie entries and eliminating anything that's not one of the recent movies. So we further restrict our list of movie entries down. And then we do one final mapping over the remaining movie entries to create an array of strings. So this style is often referred to as the more declarative style. And you see map, filter, we'll see reduce later. These are kind of the gateway drugs that most people get into functional programming. They see some code using a map or a filter. Actually, many people in JavaScript get into functional by using for each, which is very much not of the functional persuasion, because it is purely side affecting. You don't get values back from the for each method. But people said, they kind of took the drug of, I want to do functional programming. And the first thing they saw was, let me change my for loop into a for each call. But for each aside, we see map, filter, and reduce. Those kind of the typical way that people get into this FP style. Unfortunately, in JavaScript and in many other languages, even though this has an attractiveness in terms of its declarative style, it's pretty straightforward. You kind of read the steps in order top to bottom. There are some inefficiencies, and I want to call out two specifically. One inefficiency is that each of those methods, the filter, the map, the filter, the map, each one of those methods has to do an end traversal over the entire list. Now, in our example, our list is super short, so it doesn't really matter. And in fact, maybe the JavaScript engine is even doing loop unrolling or some other kind of optimization. But if the list were long enough, this could be a problem that we are, and if we have lots of steps, it gets even more, right? So you might say, well, it's all still O of n. It's not, algorithmically a more complex process, but for n is going to be slower than n, right? So we're going through this list, in this case, 4 times. That's one inefficiency that we have traded off. We started with the imperative version, we went to an abstraction, but now we've traded off efficiency. And that's kind of this very common trade off. You go for more declarative code, you often trade off performance. We're going to attempt to try to slay that performance dragon and get back to something that's declarative, but with nearly zero cost. That's the goal of the talk here. The second inefficiency that I want to point out, it's less obvious here, but the second inefficiency is that the filter method, the very first filter method, when it's called, it does not know what you're going to do with that value. So it doesn't return it in any kind of intermediate state. It just returns another full array. These are, in the functional sense, pure utilities, meaning that they don't operate on the same list. They return new lists each time. So we actually have 3 intermediary arrays, one for each of the first 3 steps. And then we get our final 4th list back that we end up console logging on the last line there. So we are doing end traversal with each step and creating intermediary arrays, intermediate lists with each step. I don't have a ton of experience with a lot of other programming languages, but I am aware that there are quite a few programming languages where if you express a style like this, whether it's method composition or not, you end up with similar performance pitfalls. Hopefully, some of you are going to recognize that in your particular language stack and say, oh, yeah, I've seen that before. I've seen those slowdowns before. Or maybe you haven't noticed, but now you will go back and try to take a look more at your code. So that is kind of our succinct problem statement. We want declarative style, but we'd like to do so with as little of that performance cost as we have to. Let's talk about another form of composition. If we had method composition before, let's talk about function composition. And this is going to be a set of techniques that we build upon to get closer to the solution that we're looking for. Composition of functions means when one function executes, it takes an input, it produces an output. That is the functional programming definition of a function, is that it's a unit of code that we pass something in, alternatively pass something in, but we always get something back out. It's not producing side effects. It's a pure utility. It's just operating on what's passed in and giving something back out. That's a function in the functional programming world, a pure function. And we can compose those pure functions by saying, I'm going to call one function and then immediately take the value of that and pass that as the input to the next. So let's see a couple of examples. I'm sorry, first let's look at a couple of utilities that we'll use on the further examples. We see a compose and a flow utility that I've listed out here, and I've reduced the style of the coding here using arrow functions and things. Some of you that are familiar with that notation, that'll look very familiar. Some of you may not like that. Mostly it was just to save space in the slides. But it is to express that what compose and flow are higher order function utilities, meaning they take in one or more functions as input and return a new function that operates over those inputs. So in this case, we're taking in a list of functions, not technically a list. We're passing in as individual arguments, but that dot 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 is gathering them into a list. So in Spirit, we're taking in a list of functions, and then we're iterating over that list of functions and taking each function call's output and putting it into the next input call, and then returning the final result. So those utilities are pretty straightforward. Almost every language that has anything concept of functional programming will have some utility. They're in almost every functional programming library. The only difference here between compose and flow is really the order that they operate on the list of functions. Compose comes from the right, so it starts from the end of the list and moves leftward, if you will. And flow starts at the beginning of the list and moves rightward, if you will. So we could call these compose right and compose left. That's another name that they often go by. All right, so here's a couple of examples. On the first line, you'll see a manual composition where I'm calling lookup movie with some input, 699 being the ID to this movie, How to Train Your Dragon. And then when I get that result back, I don't store it intermediary in any variable. I don't pass it through any other expressions. It's just immediately the input into the format movie function, which is then what gives us that string. So we see here a manual composition where one function call becomes the input to the next function call. Not very declarative, but certainly gets the job done. Anytime you see 2 or 3 or 10 of those steps chained together, functions inside of the argument list of other functions, you start to wonder, could I do a composition, a function composition here? And we see both of those utilities, the helpers from the previous slide, being illustrated. Compose is going to go from right to left. So it's going to first do lookup movie and then format movie. And then flow is going to do the same thing, but in the opposite order. So it's going to do lookup movie and then format movie. Now, you might wonder, why do we need both of these utilities? I'm not going to give you a full and complete answer to that, but I'll just give you kind of an intuition here. You notice that the compose utility, even though it's a little weird to go from the last to the first, notice that the functions are listed in the same order as they appear in the code when we drew traditional infix function calling style, as you see on the first line. So there's a value in converting our code, if we don't want to have to swap around the order, especially if it's a long list of functions, being able to use the compose utility, it kind of stays in source order. Flow has an advantage that it goes in logical progression from left to right. We generally read function programming languages from left to right, so there's an advantage there. You'll find in your programming you'll use one or the other, and not interchangeably, but you'll use one or the other in various different situations. I probably more use the compose than the flow, I think, because functional programming tends to lend itself to currying, and so you end up with a function last kind of approach. But I use flow plenty, and people who are converting from imperative code use flow quite a bit. All right, so that's working on a single function call where we had two mappers. But what happens, because we know our data flow, our composition is actually a bit more complex, we need the recent movie in there. And in fact, we also need the valid movie. But if we just insert recent movie into the middle of our composition, it all breaks. And this is a big oops. And the problem is that we cannot do a traditional function composition with things that are not mapper functions. The mapper functions that we saw before when we were composing them, that's pretty straightforward, and it's typically referred to as fusion. We can't do fusion. We can't do standard function composition because the signatures are different. In the format movie and the lookup movie, you take a single input and you get back a new piece of data. But the filter function is different. It takes in a piece of data, but it returns a true or false, and it discards essentially the data context. So it's not well suited for this type of composition. So our whole approach to wanting to do function composition as our solution kind of breaks down. So we go back, and this is back to the imperative style, but you'll note that if I just manually list out the things that I want to do in order. I list out the if statements and the lookup movie call and all of that in order as we did back in our imperative example. You'll note that I am indeed able to express a single function with no performance downside that I can pass into the map call, as you see there down towards the bottom. That single show movie function, we're doing one traversal over the list and one set of operations against it. This is effectively a zero cost abstraction for our composition. But it's not an abstraction because we had to manually write it, and that's what sucks. Now, by the way, we need that little filter boolean there because our mapper is not reducing the list when it skips over things, so we end up with a bunch of undefineds in there that we have to skip over. Okay, so we hopefully have a pretty good sense of the problem set. The problem being that we're doing an eager iteration over a list of values. We need to do multi-step, and it's kind of a multifaceted set of steps. There's some conditionals, there's some transformations. We'd like to compose all that together to get as close to zero cost abstraction in the composition as we can, but we're not really seeing that just from straight function composition, and that's where we're going to elevate to a couple of other solutions. The first solution that we're going to look at, we're going to kind of take a sidestep. It's not really going back, but it's a little bit of a detour or a sidestep into yet another performance issue that we didn't address, which was we hinted at was the idea that if we were working on an eager list, no problem. But what if it was an infinitely long list? What if it was a stream of data that was coming in? Well, our eager approach of taking the entire value set and putting it into an array, and especially recreating the array for each step and going over the entire list, that all completely breaks down. There's no way that that will work if we're dealing with infinite or indeterminate length, or really just effectively infinite. Even if it's 100 million, you're not going to want to have 100 million items in an array and redeclare that array over and over. You're just going to create way too much garbage collection pressure in the JavaScript system, other out of memory issues in other languages. So that approach won't work. Thankfully, there are lazy iteration mechanisms that are available in most languages. And in JavaScript, it's referred to as generators. Generators are in other languages like Python as well. So some of you have probably seen these before. Generators kind of get a bad rap in JavaScript. I think there hasn't been a lot of very good motivation done for why they're great. They're actually probably my favorite feature in the entire language, or at least certainly in my top two or three. Certainly, I think they're the most powerful of all the metaprogramming techniques that's ever been added to JavaScript. So if you work in JavaScript and you haven't really had a full immersion into what generators are, I hope that this kind of whets your taste for that and that you dig into it more, because I use them all the time. I think they're very powerful and useful. But we're going to use them in one particular way, which is to create lazy iterators over our lists so that we could handle something like an infinite list, a stream of data, etc. So I'm going to define two utilities, one for filter and one for map, as you might expect. That it should be pretty straightforward what's happening here. We're going to consume an iterable value by value. And in the case of the filter, we're going to do an if statement. We're going to call that predicate fn function there. And if it returns true, then we're going to yield that value out through the generator. So we're going to produce that value out. And if not, we're just going to skip it. So it has the effect of discarding the value because it didn't pass the predicate. With the mapper function, we're also going through our iterator one value at a time, and we are calling the mapper function, the fn down there, and yielding out the value that produced. What you need to note is that generators do not automatically run to completion. You have to tell them to run to completion. By default, they're going to run a single iteration and then stop and say, here's your value, do with that what you will. And then you can tell the generator, hey, give me another value. Hey, give me another value. So it's a pull rather than a push mechanism. That's what's happening here. So by default, even though these for loops look like they are eager, because there is a yield inside of them, they automatically become lazy instead of eager. And then the interface on top of the generator is what's going to do that controlling. We're not going to interact with that interface too much, but we will see a very small observation of it on the next slide. Here we are expressing the same data composition flow from before, where it kind of goes back to that more declarative, almost method chaining style. We're using a function composition with flow here, and we're calling these individual filter and map calls, those are each returning their own generator. So in other words, we are composing 4 generators together. And that's a little bit of an interesting thing because it's actually a higher order generator. But we're composing those generators together because one generator takes an iterable from another, and generators are iterables. So we're just saying the generator comes out of one and goes into the other, which is just straight up normal function composition. That flow utility is the same flow utility we saw before, works with any value. So in this case, it just happens to be working that we're passing along our iterator context. Our values will get yielded through those iterators. It's a little bit awkward how we interact with the iterator. Like the DX of the generator is because it's a lower level metaprogramming technique. You notice here that I have to wrap 699 in an array because we're expecting an iterable as the value input, and arrays are iterables, but the number 699 is not. So we need an iterable for it to first consume. And then we have, when we call show movie, it doesn't actually do anything yet. We have to tell it, give me the first result back, do the first processing through the flow. And that's when we call .next on it. So this is a little bit awkward to work with, which means that we could actually create some helpers, and we will on the next slide. But one thing to note, very important here, is that all of these generators, we got 4 generators, they are all running concurrently, and they are in a paused state after they've done each of their steps. So they are staying resident in memory and they're maintaining their own data. They're not running fully eagerly through the list and then returning a whole list. They're just running against one value and then returning that and then pausing themselves. That's what's happening with the yield, is that it's sending out a value and then pausing itself. So we don't have 4 n traversals over our list. We've gotten rid of that. And we're also not creating any intermediate lists here. So we've all automatically we fixed our 2 main pain points here just by going to this particular abstraction. We fixed those pain points. We have other pain points we'll deal with, but we fixed those pain points, and that's the key beneficial observation about the generators. Just by moving to this lazy concept, we can still use it very eagerly like we are here, but just by expressing it in this lazy mechanism, the power of the generators kind of eliminates all of the performance problems, or most of the performance problems that we talked about with the array method composition from before. So this is good. Let's define ourselves a couple of helpers to work with these generators a little better. So first of all, I'm going to have a gather function that can take a list of values and produce an actual array. So it's just that ... operator in function form. It'd be nice if JavaScript had operators as functions, but we don't have that. So then we have a take one, which is going to literally just call the .next on an iterator and then pull out its value from the iterator result, return that, and then take all consumes the entire iterator to its end and puts it into an array. Pretty straightforward helpers. We'll use a couple of those on the next slide. Here we're actually constructing the same function, but now it's a little bit easier to use. You notice that we've inserted a step of gathering as the first step in our composition, and then at the end we have the take one. So we, in this case, we know we're just going to pass in a single ID for show movie, and it gives us back that single string as the result. So now it's a nicer function for us to use without worrying about the underlying concepts of generators in that interface. We can then lift that to the context of the entire list. Here's back to our kind of original example now, where we're going across the entire list of movie IDs. It's a straightforward process to kind of lift that concept, because we can do a flow control. We can do a flow composition over those lists. And at the end, instead of using take one, I'm going to do take all, which is I'm going to consume the entire iterator context I've been passed and put all of that into an array. So that's the key difference between the two. And also, we didn't need to pass in the gather step this time, because we're going to pass in, as you see there, the flow function returns us a composed function, and then on the very next line, we just call that composed function with our movie IDs list. Again, keep in mind that the array is automatically an iterable, so it can be consumed by our iterators or generators here. Okay, so this really has actually moved the ball forward, and we didn't have to do hardly anything. We just had 2 very small little helpers that we defined, we had to change our context, our mental context, to working in a lazy form. But we're doing an eager iteration with a lazy mechanism, and it works great. And it has, again, gotten pretty close to a zero cost. Not fully, but pretty close to a zero cost. Now, you might be wondering, well, if these are such great little helpers, why aren't they just built into the language? And people have been asking for that and for other helpers like that for quite a while. Besides the map and the filter one, there was about a dozen others that we've been kind of begging JavaScript to finally add. And great news is that they did add those to the iterator interface. That landed, I think, last year. So it's pretty standard across most modern JavaScript environments now. So we have these built-in iterator helpers. We don't need to define our own little map or filter function. Now we can just use them directly on our iterators. And I want to point out I've used a couple of terms that sound interchangeable, but just to keep the terminology for JavaScript straightforward. In JavaScript, an iterator is an interface that produces values. An iterable is an interface over the collection of values. So it's like the data structure itself. Whereas an iterator is the thing that is going to process and potentially produce value. So those sound like almost the same, but they are distinct concepts here. So an array, for example, is an iterable, but a generator is an iterator. These helpers help us work with generators then, because these are iterator helpers rather than iterable helpers. So just keep that straight. We still have all of our normal eager iterations over array lists, the iterable helpers, if you will, like map and filter and reduce. We still have all of those, but we now have lazy versions of all those on the iterator interface through generators. By the way, if you want to read up on that proposal, it's already been added to the spec. But if you want to read all the discussion of that and go through all the lists, the issues list, and see how they came to these designs, that repo is still actually really valuable information to learn about. But here is our running example expressed with the built-in iterator helpers. The only difference that you see now is that we've switched back to a method style of composition. And you'll see on the first line, we're doing iterator.from, which is going to turn our iterable, the array movie IDs, into an iterator, a function generator. And then on the very last line, we've got the toArray, which is going to go in the opposite direction. The toArray function takes us from an iterator and potentially lazy infinite iterator down to a finite, fully consumed array list. So we go into the iterator, we do our composition, and then we step out of the iterator back to an array. Even though those method calls look the same as the array method calls, they don't have any of the downsides of array method composition, because under the covers, these methods are doing that same context sharing through the generator interface that I showed a couple of slides back. So we've gotten rid of all the multiple end traversals. We've gotten rid of the intermediary arrays. The one downside that we still have, which is unfortunate, is that the generator interface is a bit complex because it's such a powerful metaprogramming tool. And we have one instance of the generator for each of our steps in our composition. And many times our steps of our composition are not just 3 or 4, but they can be like 10, 12, 20 steps for modern complex apps. So all those generator instances are hanging around in memory until the entire iteration is complete. And there is a bit of inefficiency to yield a value out and consume it through the generator interface. So it's not zero cost. It is better than what we had before. It is certainly an improvement, but it is not zero cost. So it doesn't fully represent the solution that we were hoping for. The good pro, of course, is that this mechanism is extendable to the lazy infinite list scenario where our other solution was not at all. This fully works the same whether you're working on a finite small list or an infinitely sized lazy list. Okay, but I've been hinting that there might be something that's going to get us much, much closer, if not exactly to a zero cost composition abstraction. So let's dive into that. We're going to use this other technique, which I'm going to forewarn you, if you haven't looked at this before, it might be a little bit mind bending. Certainly took me a while to dig into this code and take it apart and rewrite it myself. But these utilities are actually not that complex, and they're small enough and straightforward enough that I'm going to be able to fit them all on one slide. So there's not some hidden magical library that's a framework that's going on. It is straightforward enough to go on one slide, but you do have to kind of get your brain wrapped around this mathematical trick of transducing. So before I even show the code, what is a transducer? It is a higher order reducer. You know, a higher order function is one that takes functions as input and produces new functions. Well, a higher order reducer is a function that takes reducers as input and produces another reducer. And you probably, hopefully, remember what a reducer is. A reducer is just a function that takes an accumulator and a value and combines them, right? So we're just talking about a higher order version of those. Transducers are higher order reducers. And the trick that we're going to get here is if we can represent all of our steps of composition as these transformed reducers, as these transducers, then we'll be able to compose them all together in one single big chunk. So it'll be a one shot that will do all of our steps, kind of like our imperative show movie function that we had illustrated before. So we're doing a mathematical transformation on these things instead of having to manually and imperatively write that function. Just we'll check, make sure. All right. So here are the utilities that I was referring to. This is basically the heart and soul of what transducing is. Represented, of course, in JavaScript, but small enough that you can actually see it formatted out on just this one slide. So we see mapt is a utility that takes in a mapper function like um, the format movie that we talked about, or the lookup movie, those mapper functions is its first input. These are just manually curried things. So if you're not familiar with that notation of the arrow functions, I just put each step on one line so that it's clear because I get lost in all the arrows when they're all on one line. So that's why I've broken them out onto multiple lines here. But the first step is we're going to pass in a mapper function and we're going to get back a function that expects a what I'm calling a combiner function here. That's just a fancy way of saying it expects a reducer. So when I call mapt and I pass in something like, for example, format movie, I'm going to get back this function that expects combiner function. That thing is a higher order reducer, aka a transducer. So mapt is not a transducer, it is a function that will produce a transducer. You give it a map function, you get a transducer back. Same way with filter t, we pass in our predicate function, we get back a transducer that's expecting a combiner function. Higher order reducers here, once they get their reducer, once they get their combiner function, they produce a new reducer. And you'll see there that the last line of each of those functions is a standard reducer. It takes an accumulator and a value. And in this case, for mapping, it maps the value with the mapper function. And then it combines that with the list using the reducer that's been passed in the combiner function. So I don't do like list.push here. I'm just doing list and mapper of fn of v and telling the combiner function, you figure out how to put those two values together. So there's a little bit of an abstraction there. Same thing with filter t. I call the predicate function. There's a ternary there. If that passes, I pass the value and the list into combiner function that I've been given. Otherwise, I just return the existing list because I didn't need to do anything with that value. So it discards it. Transduce L, meaning transduce for lists, is a higher order function, of course. It takes in a function. In this case, that fn there is a transducer. So it takes in a transducer and it calls that transducer, you'll notice there in the next to last line, with concat L. Concat L, you'll see on the very last line, is nothing more than a list concatenator. It just takes a value and concatenates it on, appends it to the end of a list. So when I call fn with concat L is the combiner function of our composed transducer. And so that's the ultimate thing that comes in and says, hey, when we get these two things and we need to stick them together, the way we stick them together is just shove values onto the end of a list. And then I take the result of that transducer call, the fn with concat L, that just produces reducers, right? A higher order reducer, a transducer, it produces reducers. Well, I get a plain old simple reducer that, by the way, has all of our steps already composed into it. And then I just do a single reduce call. So that reduce call in the next to last line is the magic. We're going to go once through our list and we're going to do all of the work in one function call that is our one big mathematically composed reducer that we got back from our composed transducers. Lots of words that I just said. I'm going to encourage you. You'll probably want to go back and reread some of this information, go re-listen to this recording. But let me just show you how that looks in our code, because it's going to be, I hope, a lot more graceful than explaining how transducing works. So you'll notice, first of all, in the innermost part, we're using compose, kind of like we were using flow before. I'll explain why we switched. But we're just doing a composition of these things. Now, remember, filter T is going to give us back what? It's going to give us back a transducer. So we're basically composing 4 transducers together. And you remember that a transducer is a higher order reducer. It's expecting a reducer as input. So at some point, we're going to need to pass in a reducer into that composition. And then those reducers are just going to produce another reducer, which produces another reducer, which produces another reducer. And we get back one giant reducer. That is our composition. And that thing is what we're passing into transduce L, that transducer that we're passing in to transduce L. And transduce list, transduce L, you remember it takes a transducer and it passes in under the covers the concat L utility. Because we can do transducing for all kinds of values, not just for lists, but here we're doing it with lists. So I'm just kind of simplifying. We're transducing with a list, so it's kind of hardwired to use the list concatenation to do its work. And transduce L produces one function who's expecting a list of IDs, which we pass in as movie IDs, and we get back our finished list. So what we have now done is taken our existing application code, the valid movie, lookup movie, recent movie, format movie. We have mathematically transformed those into reducers, into higher order reducers called transducers, composed all of those transducers into one big transducer, taken that transducer and made a reducer from it with the list concat, the concat L utility, and then done a single reduction over the movie IDs list to get back our newly reduced and transformed list. We've done all of that with one single n iteration through the list, so we don't have multiple n iterations. And we've done all that with no intermediary arrays because it's just one giant function that's operating on each value. So we now have gotten back to the same kind of zero cost promise that our previous attempt with the lazy generators gave us, but we do not have anything sitting around in memory with these complex interfaces of generators. You saw the entirety of transducing on the previous slide. There's nothing else to it. It's just those function calls. And by the way, if I were to go back to that slide for just a moment, one thing I forgot to point out, you'll notice that each of our 2 reducers, look at the list that says combiner function, list mapper function, and then the one that says predicate fn with the ternary. Those 2 lines of code, those are what we call tail calls, meaning that the function call stack is at the end of the function call. And in JavaScript engines that have implemented tail call removal, like for example, Safari in strict mode has this, then it will literally at the compiler level optimize away all those function calls and it'll just be one single set of code with no function call overhead at all, literal zero overhead abstraction. I wish all the JavaScript engines had implemented the proper tail calls, but we at least got one of them. We know that Safari did it with the strict mode. And I'm hoping someday, maybe if more of us functional programmers keep begging for it, all the other engines will catch up. But what we've got now with our transducing is kind of our magical unicorn solution. We have a declarative approach that uses functional programming techniques, and it removes, because of the way that the transformation works, it removes the inefficiencies that are inherent to this type of composition. So we get almost a perfect zero cost abstraction with only having to pay a couple of function calls in the list instead of having to pay for n traversals or all those intermediary arrays and garbage collection and all of that. So that's a really great outcome. It did take us having to wrap our brains around a slightly more complex technique, this transducing, but hopefully it's not too intimidating and you can dig in a little bit more. I have one last thing I'm going to finish with, one last kind of bonus that I'm going to finish with, which is that we've been talking this entire time about synchronous composition and synchronous data processing. But what about asynchronous processing? I said that we kind of faked it with the lookup movie being just operating synchronously over an existing in memory data. That's not how our real applications are going to work. It's going to be making a fetch call to an API or whatever, reading something from the electric SQL database that James talked about, something. It's going to do something asynchronous. And we still want to be able to have all the guarantees, all the nice declarative abstraction, and none of the performance overhead. How do we do that? Because none of what we've shown so far seems to lend itself to asynchronous programming. You might guess that the reason why I'm talking about this is because there is a solution where we can extend all of these concepts, even transducing and composition, into the asynchronous space. We can lift everything up in JavaScript terms, lift everything into promises. That is a bit more complex than what we're going to go through in this talk. There are some gotchas that we have to worry about when we're lifting everything into the promise space. And it's not the kind of thing that you want to inline the code yourself. It is the kind of thing that somebody needs to implement in a really nice, clean, simple library. And hopefully, you're going to enjoy the fact that I created such a library. And so I'll show you that library. It's called FACY. FASY. It stands for functional asynchrony. So let's take a look at how we would use the FACY library to do our same example with transducing. So we get the zero cost abstraction, but we can now work with it over asynchronous methods as well. You notice at the top, I'm importing the serial interface for composition and the transducers interface to be able to work with this. There are other things, of course. FACY supports both serial and concurrent compositions and iterations. So you can go and take a look at all the different things that you might want to import. But here I'm just using a small portion of the library. We're doing a straight up normal compose. That's what fas.compose is. And then we have our 4 transducers represented by the fat.filter.map.filter.maps. So we're doing our same composition. I'm using the into method, which is a slightly different way. It's kind of like the transduce L, but it's a little bit more generic because it's saying into what. And in this case, we're going into an empty array as opposed to into a string. If we passed it an empty string, it literally would have done the exact same thing, but it would have string concatenated rather than putting separate entries into an array. So that shows you that transducing is more general than just list processing. But the real key thing here is that if valid movie or lookup movie or any of these steps are asynchronous, this code just magically keeps working because it's all been lifted in the promise space. And we see that final await call there, awaiting the result of the into method. When that promise resolves, all of those steps will have finished. And so we don't have to worry about any of those problems. We couldn't do any of the asynchronous processing with any of our previous examples, list methods or the generators. They don't automatically deal with the asynchrony, but here this FACY library does handle that complexity for you. And it provides you the composition and transducing that we talked about. So it's kind of the best of all possible worlds. So the last thing I'll point out is that even though this is designed to work for asynchronous operations, you could literally use FACY for purely synchronous operations as well. Because under the covers, it's just lifting everything, so it won't matter. Slight overhead of dealing with promises, but it'll have the exact same capability. So you could just standardize on using FACY for both synchronous and asynchronous transducing and composition. Mix and match as your application sees fit. I use FACY on quite a few of my projects. It's been around for a number of years. I have no idea how many people have also found it because I don't market a lot of my open source projects. But hopefully those of you listening here today are intrigued a bit and want to go check that out. So that's what I've got for you. All of the code in those slides, because all that was very heavy code, that's all up on a gist, and you can get that from the QR code there. And then my slides today, the QR code on the right will provide you a link to those slides. Thank you all very much for listening.
Thank you very much, Kyle. That was very nice explained. Like, like this is here you have the loops, here you don't have the loops.
Right.
And really
Well,
like
you
going
have the
through
loops,
it.
but they're buried below, right? They're
Exactly.
handled by somebody else. You don't have to write them. Yeah.
Exactly. Very nice. Very nice. Um, um, Question from the chat. As someone who doesn't do more JS than I absolutely have to in my job, what are some of your favorite features which might make me a bit more keen on it?
I already mentioned one of those, which is that I love generators and being able to handle the complexity of that. The main thing that I like about JavaScript is one of the main things that most people dislike about JavaScript. So I'll be slightly controversial here. I actually think that JavaScript's type coercion capabilities are a very key core strength of the language. The vast majority of the modern development community says JavaScript types suck, they're poorly designed, they're buggy, they're horrible, and they've even invented whole new languages like TypeScript to slap
Mm.
on top just so that we can never have to worry about any of that stuff again. The one point I'll make about that is that you cannot get away from the fact that your code is running in a JavaScript system. And even if you write TypeScript, you're going to have to deal in certain corner cases anyway with JavaScript's coercion capabilities. So I would actually recommend you should really lean into that rather than trying to hide it away as much as possible. And so that's one of my favorite things because I don't worry about those problems because I learned JavaScript coercion and I don't need things like TypeScript to help me be type aware. I've just learned the rules of how JavaScript's mechanism works. So I know that's a very controversial take that I'm just about the only one who will say so, but I really do think that JavaScript's coercion system is a strength. And then I guess I'll just pull out a slightly more modern feature that came in. We added optional chaining, which again, if you're a functional programmer, you're used to working with things, maybe used to working with things like monads. It's not actually the option or the maybe monad, but it's very similar in approach, and it still kind of marries to the imperative style of dot operator data access, and it just uses a nullable check on that. I'm actually a big fan of that because there's a whole lot of really imperative if checking guards that you have to do to get around that problem in JavaScript, and they landed that one operator, and most of that code just got deleted. So even without having to go all the way up to monads, we got a big capability just by that one tiny operator. So off the top of my head, those are the three that I would say are very attractive about JavaScript. I don't know that they're going to pull anybody from some other language to JavaScript, but if you're in JavaScript or JavaScript curious, I recommend at least doing a little bit of studying that. By the way, in coercion, I read a whole book about that. It's up on my GitHub. So if you want to read more about my thoughts on that stuff, I've written quite a bit about it.
Thanks. Next question. Is RxJS a similar library?
Ooh, no, it's not a similar library. There, that's kind of like asking, is this Titanic the same thing as my apple in my hand? They're very different things,
Yeah.
and RX is very much bigger and more complex and does a whole lot of things.
Mm.
You probably could represent at least some parts of the examples from today using RX, but you absolutely would not get to essentially a zero cost abstraction the way that I tried to show.
Mm.
So you pay the penalty of staying in their abstraction layer. You're getting all this extra power, but if you don't need it, you really should not be using something like RX. But just for the audience's sake, RX is a it's the observables pattern implemented in a bunch of different languages, including the RxJS, the JS port of it. So it's these complex concepts, but it really boils down to the ability to have streams of data that you subscribe to or that you push data down. So you get both a push and a pull interface over streams of data. That's kind of one of the main ways that people do streams based programming or kind of observable based programming in JavaScript. There have been some attempts to try to add something like that into the DOM API standard, and therefore it would kind of come for free in JavaScript. I don't know where those stand, but RX itself is a pretty big and complex library. It's a lot of learning. And everything that I showed you here today, with the small exception of Facey, everything I showed you here today fits on a slide. So I prefer small mental
Mm.
context rather than take on the giant mountain to do one tiny task.
Yeah. Next question: how does failure in the async stream be handled on any one of the pipe function?
Ah, so if we're talking about FACY, the way failure happens at any point is that it's lifted to a promise rejection. So you handle that, you receive a promise rejection in the same way that you'd handle any other asynchronous rejection. If we're talking about in the transducers or the other function, uh, uh, you're going to get a synchronous exception in your call stack, and you are unfortunately going to get a really complex call stack with all those intermediary function calls
Mm.
happening. That's one of the reasons why I was referring to the idea that having the zero cost abstraction um, from the tail call elimination is so beneficial, because in a language that supports that, or I mean in an engine that supports the tail call elimination, you would actually theoretically have all of those intermediary functions not even show up in your call stack, because the JavaScript engine treated them as if they didn't happen, um, because it kind of did all the inlining and stuff. So that's the reason why we want zero cost function calls, and the zero cost abstraction is actually not only for the performance but for the debugability. It is more complicated to, well, just it's more tedious to go through these long call stacks and filter out all the stuff that's just those intermediary function steps. Other languages besides JavaScript have strengths there in that their compilers do a lot of that removal of those layers, and JavaScript doesn't, unfortunately. But that's one of the reasons why I highlighted the tail call positioning of transducers, is that they at least make themselves friendly to that. If we could get more engines supporting it, it would be a much improved debugging story. And then the same thing with generators. Those act, even though they look asynchronous, they act synchronous. So you would just, even inside of the generators abstraction, you would end up with a synchronous exception reported in your, with a call stack or something like that. Modern JavaScript environments like the browsers and Node and stuff support asynchronous call stacks. So even if it was across asynchronous steps, you would still get a full call stack there. So that's the difference between phasey. You would get it as a promise rejection. Everybody else, you're just going to get a big, tall stack exception list in your console.
Okay, thank you very much again, Kyle. I have one last question. How come you get into this? I mean, if you work with JavaScript, the typical JavaScript developer I know, they don't at all view this or try to get into this type of optimizations, etc. Or don't at all like this function compositions you have done.
Yeah. So my answer is that my ultimate goal is to write the best code,
Mm?
not to write the most popular code. I've never been driven by what is popular or what is marketable. I've
Mm?
always been driven by what is the most correct. And I think everyone in this audience, since you're a functional programming community, you'll agree with the sentiment that, at least for me, the main attractor to functional programming is that I don't like writing code that I don't understand or that I'm not sure what it will do. I
Mm.
do not like the cycle of write some code and then cross my fingers when I run a test case to see if it passes. I want to write code that I understood, that I intended, and that I am certain will produce a certain an outcome. That doesn't mean I'm going to write bug-free code. I'm going to write bugs, but I don't want my bugs to be around things that I very much could have had understanding over. In other words, I want to reduce the surface area of where my bugs can happen. And ideally, I want my bugs to be business logic bugs rather than programming logic bugs. And that's
Mm.
the attraction to me of functional abstractions. It's one of the reasons why I'm recommending that modern JavaScript do away with all the frameworks and go towards a more monadic approach. And I'm the only one out there saying that, because everybody says, well, if you want to do monads or whatever, go to some other language. I think front end programming and JavaScript and web app programming would benefit from embracing these ideas. And I went on that path of trying to learn how these things work. It was not an easy path. I don't
Mm.
think there's a lot of great resources there, but I wrote a whole book about embracing functional programming in JavaScript and embracing what JavaScript is, but also bringing in the functional approaches to it, because I believe those two things can be married together. And I tried to leave that as kind of some better breadcrumbs for folks that want to go on the journey. But ultimately, you have to decide that You're not going to wait for some other framework author to solve the problems that keep plaguing your app. And I think that's what most developers are doing is we're just waiting for the next better silver bullet, the next version of React or the next Vue or the next whatever. It's going to fix all my problems, and it's not. Uh, there is no singular tool that's going to fix those problems. Your knowledge is the only way to fix those problems. And I've dedicated my career to helping kind of voice the need to move in that direction. I chose JavaScript a long time ago, and I haven't needed to move off of JavaScript, although I have interest in other languages as well. But I don't feel like I need to leave JavaScript behind because JavaScript is completely incapable. I can advocate for doing things in JavaScript a different way. And that's one of its strengths is that it is so malleable. You can do a lot of different styles. And I think among the infinite ways that you can express a program, there is a subset that's a lot better than the rest.
Mm.
And that's what I've been trying to attract more people to. You know, the final thing I'll say about JavaScript is it's not the end all be all language. I write it every day because it's a very powerful tool. It's malleable. It allows me to do a lot of what I want to do, but it's not everything. And I've made a lot of complaints about JavaScript over the years. I've said my piece in social media about what I wish they would do differently. I've advocated for changes. They've never listened to anything that I said. I'm just some outsider who has opinions, and I don't get to influence JavaScript in that way except through, the knowledge transfer with my books or things like that. But um, I decided a couple of years ago I did not want to spend whatever's left of my career complaining about JavaScript. I instead wanted to be part of building something that I thought could be better and could solve things, not to replace JavaScript, but to augment our options. And so I started designing a new programming language, a functional programming language. And I have a full design for that. I'm working on the tooling to spin that up and bring that out. If any of you are interested, it's called FOI, FOI, and you can find that out on my GitHub. Maybe it's a great language, maybe it's a terrible language, but I'm at least, instead of just sitting around and complaining about what JavaScript isn't, I'm trying to design something that I think is what I wish a language would be.
Thank you very much, Kyle, and thank you very much for your elaboration. Thank you. And again, we'll put out all the links and everything once we're done with the live streaming. We put it out everything below the video, so you can find to Kyle's and to James' different libraries and to slideshows and etc. Again, thank you very much, Kyle, and thank you very much, everyone, for this kickstarted first Func Prog Sweden of the year. And see you next time in February. Until then, have a nice time.